my screen? You should all be seeing my screen right now. Please unmute if you can.
Yes, you can.
Okay. Okay, thanks. Okay. All right. So we are currently here in Introduction to Machine Learning, and we have the slides and the notes. And I'm going to be going over the notes. I was going to go over the slides, but I felt like we might not get to the notebook. And we did a lot of theory last week, so I felt like let's just do some practical work today. And I'll try to go as slowly as I can. And if I'm too slow, let me know. If I'm too fast, let me know. If you don't understand anything at all, please unmute yourself to say something. And Genevieve, you would be my teaching assistant today. So it means that if I'm like, do you understand something? Do you not? You can help coordinate the response on chat because I might not see it. So, and then we can, if anyone wants to say something, like I said earlier, please feel free to unmute yourself. So we started with this question. Why do we need machine learning? So we know that we have classical programming, right? Where you write a function to do something specific. And this, like most of us are familiar with, say, for example, you want to write a program which is like a recipe for something, and you're like, how do I bake cake? So you have, you can say, have flour, sugar, whatever, like with the right measurements. So that's like you writing an algorithm for you to bake a cake. But coming to the problem of machine learning, I'm going to start by introducing the classical digits recognition. So I have a question for you all. Let's say you're tasked with this question. You have a bunch of numbers and you'd like to write a program to recognize the number. Like, I'm like, hi, Genevieve, can you write a program that can be able to recognize digits from 0 to 9? How would you write the program? Anyone can answer. We can just like take two answers. I can see your hands up. Chidima, would you like to say something?
No, that was a mistake, sorry.
Okay. So did you all get the question I asked? Hello. So my question is that if you have a digit from 0 to 9 and someone asked you to write a program to recognize these digits, how would you write the program? What are the things you would need to be able to recognize that a 1 is a 1 and a 2 is a 2?
My check.
Okay, you can say something.
I think I would have a bunch of if statements for each letter and for each number.
Exactly. So what are the things your if statement would contain? Like, if, do you want to walk us through your thoughts, maybe for one of the digits, if not all?
Okay. I would get all various samples of, let's say I have to, for number 1, I'll take various samples of how number 1 can be written down and have a bunch of if statements and say, if you see this particular number written this way, it should be number one. And I'll do the same thing for all other numbers, and it will be so much. And as I think I'll go about it.
Yeah. So you might think about it. You might be like, if you find like a stroke that looks straight, that blah blah blah. Like an easy example would be write an algorithm for detecting a table. You might say if you see 4 legs, then it's probably a table you get, or all this other stuff. But then your algorithm is going to break once there is some sort of table where like people just put it flat on the ground, but it's still used for eating, and it's still considered a table, and it doesn't have 4 legs. So what do you do about that? Or how are you able to account for such different cases? So that's one of the very, very big problem of that the machine learning could help us solve. Like, so machine learning is the should I say method, or method is not really the right word, but anyway, so it's in its core, it's data-driven way of writing a program. So you can think of it of being able to write a program like without you explicitly stating all the rows. So, and the example I asked you was the example that was given in the course, and I'd assume some of you have gone through this lecture notes, but if you haven't, I would highly encourage you to do so. Anyway, does anyone have questions with regards to why the motivation for using machine learning? Because that's basically what we went through last week. I'm just reiterating and trying to set the floor for upcoming discussions. Any questions so far? Any questions so far? Oh, okay. Charts. Does anyone have questions so far? Please use the chat. You can either answer yes or no. If I see, okay, yeah, cool. Thank you. So moving on, the example we'll be working through today is the predicting peak electrical power. So the problem statement here is that, let's say, so what happened is that there are data sets, and okay, let me kind of like explain the problem statement. So the reason why we might be interested in predicting peak electrical power is because basically, according to data sources that was listed in this note, so it said that usually electricity they need to generate electricity. So you need to have like excess before you can be able to do more things. So basically we need to know, we need to be able to forecast future demand so that we don't have more excesses. And so the question is that, when do people use a lot more power, and how do we account for those kind of situation? And you can see from here that the better we can forecast future demand, the smaller our excess margin can be, leading to increased efficiency of the entire electrical grid. And that was what motivated this particular problem, and why we want to build a machine learning model that we can use to predict peak electrical demand. given temperature. Let's say you have this temperature, what would be what's the predicted electrical demand? So in order to do that, we're going to be relying on some available historical data. And luckily or interestingly, there were a lot of data sets. I haven't looked into Nigerian electrical data sets, which I would encourage us all to check. And I would also see if there's something on it. And we could try we could use the same notebook the same knowledge we'll gain from this notebook to build a model to forecast such data sets, such Nigerian localized data set. But for now, we're going to be using the Pittsburgh PJM dataset. So last week, Kenichi mentioned that he found the data that the website the data was previously hosted has changed. So now he was able to download the data. So I just got I cloned the repo. If you don't know, you can go to GitHub and clone this repository. That's Kenichi already put it there. So I just cloned this repository that has the data set. That's what we'll be working with today. So sorry, I think it was there just now. Oh yeah, so this is the data. We have from 2013 to 2017. And you can have a quick look right now. You can see that like this is CSV file, and this is what we'll be working with. So the first thing we'll try to do, because of course we've been trained as a data scientist, it means that we can source for data ourselves. We would start from finding the data, joining different data sources together, cleaning data, the barest minimum, not so much. So let me just run this. So I have this data set somewhere here in my it's not in the same directory I'm working with, so that's why I have this here. And usually I find it a lot easier for me to understand parts of what's happening. So if you look at the original notebook, I have tried to make things like run things cell by cell so you can see what's going on, and it doesn't seem like things are just flying around and you can figure it out. So basically, the first thing we want to say is that there's this glob.glob. I'm not going to be going through that. And I'm going to assume some of you know what it is. For many of us that haven't seen it before, this is the first time you've seen it. It's a very convenient way for you to read file paths like directories and all this stuff. So, for example, what this particular cell is saying is that go to this directory. If you find any .csv file, then list it for me. And this is exactly what it's going to do. So you can see that right now, each file name is just the CSV file, and then it's just listing the file path for me. Is that clear? You can use the chat. I can see the chat right now. So just let me know if it's clear or not. Please use the chat and let's try to make this as interactive as possible. Thank you, Genevieve. So the next thing we want to do is to read each of these CSV files. So how do we do that? I wanted to show you at first, let's say we want to read just one of it. You know, right now we have 5 CSV files. So we could say something like, oh, let's read this one by one. We do PJM 2017, we do for 2018, and then we just read it one by one. But that would be, I mean, that is not bad, but because we are bad as data scientists, and we know how to use for loops, so why not do it? And I just wanted to show you what it looks like. If you just like pick one of the data parts, you can see what I did here. This is the data part, which is what I have here. And then I just joined it using the screen. I concatenated right out with this, and then that's the concatenation. And I just read it using pandas. How many of us have used pandas before? If you've used pandas before, can you put it on the chat? Okay, so we have a couple of people who have used pandas before. That is great. And so the next thing after we do that, so this is basically the whole process. We just, the first thing we want to do is that we want to load in the data set, right? And this is the function that is doing it. So we are loading in the data sets for the electrical demand, and then we are going to, because I told you that what we want to do is that given temperature, we want to know like what's the maximum electrical, like what's the maximum peak demand for that for a particular day. So that's our problem statement, nothing more, nothing less. So for us to be able to do that, we are assuming that we have access to temperature, like each day's maximum temperature, which is true, because we can get access to weather temperature. We can know what was the peak temperature for each day. So we need to combine those two knowledge in some way to be able to predict what would be the peak usage in a day. And is that clear so far? Do we have an understanding of what the problem statement is at the moment? Thank you, Blessing. So I already went through this. So now what we've done here is that we've loaded all the CSV files. And then what we've done here is that we've also loaded the weather file. So I'm just going to show you what it looks like. I already showed you what the PJM electrical demand files CSV looks like. So we just take a peep look into the weather data. You can see that there's something common with the two. They both have its time column. It means that, okay, we could do something with that. So the next thing we would like to do, normally when you're dealing with something like this, you would want to investigate your further by doing some data cleaning. You want to know if there are empty rows, if there are if there are some things that are not supposed to be in your data. Like basically you just want to clean your data. You want to make sure that if there are like if some columns are not filled, then you want to decide whether or not to drop the entire row or whether or not to use some techniques to fill in the missing cell. So we're not going to be going through all those. We're going to assume that your data, the data we are collecting, is clean to some extent, but that's not quite true. So we'll see as we go. So the next thing we want to do is that let's try to rename like the dates column. So I'm just going to, what this is doing right here is that it's saying that we want to have another column called dates. And that column is going to be targeting the date time beginning UTC column. And all I want to do is that I want to reformat it to look like what the this time column is on the data frame weather, like the weather CSV file rather. So this is exactly what we're doing here. And then we can look at what it is. Okay, because I'm applying, so like, you know, it's like if it's not like, it's basically if it's looping through each of it and trying to apply this. So that's why it took a couple of seconds. So you can see it right here that the dates column looks almost identical to the weather file, weather data time column, almost identical. If you look at this weather time column, you would see that the only difference is that there are these extra 4 zeros that we don't necessarily need, right? So we most likely should get rid of them because it doesn't do anything. So we can see that this is date, this is month, and this is the day. Excuse me. Excuse me. Sorry about that. So going to the next thing. So the next thing we want to do, because like the data science data science course .org, they've been so kind to go through the data, and they've realized that there is something still dirty about the data set. So the weather data set has like the time column as -999. So we want to make sure that we don't we don't put that in our file, in our preprocessed CSV, like preprocessed file for, that's not the right term, but in our preprocessed data for analysis. So we want to make sure to remove that. And how do we know that it's dirty? So you can just like do a quick look. If you look at this weather data here, and you say that if this is exactly equals to -999, you can see this is not a data, like there's nothing here. This is pure noise or something. So so we want to make sure to get rid of that, and the way to get rid of that is to filter it out by saying that just get me anything that is not anything, this data frame, but make sure that it is not, we don't have the time column does not equals to -999. It's just like basic filtering. So what that would do is that it would give us the same data frame, but without these three dirty data. So, and the next thing we want to do once we do that is that we want to make sure that we remove these 4 zeros from it, which is what we are doing here. If you look at this, so we are saying that look at the time column again and apply this function. And this function, this lambda function, is just saying that for each string, each of this guys here, for each of them, make sure that just cut it off at like the 8th character. So it will be from 0 to 8. So it will actually be, sorry, from 0 to 7. It won't quite get to the 8th character. So if we just count it here, like 0, 1, 2, 3, 4, 5, 6, 7. So once it gets here, oh, no, that's wrong. 0, 1, 2, 3, 4, 5, 6, 7, 8, actually. Okay, so this is 01, 2013 01. No. Yeah, this is it. So this is correct. Yeah. So you want to you just want to pick 2013 01 01. The same thing here. You want to pick 2013 01 01. So you want to discard the rest of this. I made a wrong statement earlier when I said the last 4 digits. It's actually not just the last 4 digits. It's like the last 2, 4, 6, 7. The last 7 digits that are not useful. So anyway, we want to cut it off before we get to the 8th character, which is what we're doing here. And things at the molar 0 to 7, yeah. So once we do that, you can see that the dates column is for the weather data set is now identical to the dates column of for the what's it called again? Electrical demand data. Yeah, this is where you tell me what it's called. But most of you are muted, or all of you are muted. Anyway, so far, are we following? Am I too slow? Am I like, I can't be too fast. I can only be too slow. Is it clear so far? Shall I move on? Okay, thank you. So the next thing we want to do, we're getting there slowly. The next thing we want to do is that we don't necessarily need all these columns. I mean, they're useful in their own way, but for our simple, I mean, don't let me call it simple model, but for the model we want to build right now, we don't need all these features to make a prediction. And we're just going to pick the ones we need, which is exactly what we're about to do here. So what we want to do is that we want to look at the electrical PJM data, and we want to group it by date. So for context, this is the data I'm talking about, this one right here, this TF load. So we want to look at the data, and then we want to group it by this date column. So why are we doing that? So the reason why we're doing that is because if I come back to show you something, just let's look at this. I'm going to pick the data, and then I'm just going to come here, and yeah. So if I just pick 2013 January 1st, and then I show you what I look at what happened. So you can see that on this day itself, we had a lot of data for that day, but that's what we want is to look at the maximum estimated load hour for that day. So we just want to know at what point did our load hour increase, and then we want to also look at the temperature for that particular day at that particular point. So if we look at this, just like put this in mind while I show you the other one as well. So if you come here to look at the weather data rather. So for the same day, like this is the same day, 2013 01 01, January 1st, 2013. So you can see that for this day, this is the temperature column 008. So you can see that for this day, the maximum temperature, of course, seems to be like either of these two, because the rest are just negative temperature. So like this is like the highest temperature for that day. So and then so we want to look at the highest estimated load hourly for that day as well. And from what we are looking at here, it seems that it's this one, right, guys? Is that right?
Yes.
Exactly. So from this table that we have right now, it seems like this data is the highest for that day, and so that's what we want. So our hypothesis is that we are saying that we are assuming right from onset that the highest temperature for the day corresponds to the highest the estimated load hour, like our estimated load hourly, the maximum of it. And if I make any error, like just feel free to correct me on the chat and something. So let's move on to the next thing. So that's what we're trying to do here. So we'll group by the dates. We'll look at the maximum, and then we'll just we will, like, because we're grouping by dates, and then looking at the maximum of it, and we are taking out this particular this particular column, and I'm going to show you what it looks like, and we're saving it in a data frame load new. So this is what it looks like now. So you can see now, instead of having like all this data, we now have something we want to work with, which is just two columns: the dates, that has the date, and then it has maximum, because it's the same thing as the estimated load hour. I just renamed it to max. So the next thing we want to do is that we want to do the same thing for the weather data, but in this time around, we want to pick out the temperature column. So we're basically doing the same thing, and then we are converting it to Celsius. So it's like much more relatable. So if you look at what this is, you can now see that we have this is the original data. Now we have temperature. So 0 Fahrenheit. This should be Fahrenheit. So so 0 corresponds to like 32 degrees Celsius. Is that clear so far? Okay. So thank you. So the next thing we want to do now is that we're almost there. You can see that most of what you do in machine learning, I mean, if you're not doing research where you just like get clean data or other stuff, and you don't bother about all these other things, for real world, real life machine learning, you have to collect your data, clean your data, reformat your data to what you want. Then, like, basically you need to prepare your data for your model, because your model is just as good as the data you feed into it most of the time. So, I mean, even without you tuning or doing any other parameter search, you feed in like good data, like, and we'll define like what we mean by good or bad. It's just like a data that you can learn something from, that there's a correlation between like the features and the between the features and the labels. So it's almost possible for you to be able to find like a combination of the features, or like a single feature, to like be able to make some prediction. In this simple example that we have, the feature we have is enough, like just the one feature, which is the temperature feature, is enough for us to be able to make this particular prediction that we are about to build a model for. So the next thing we want to do is that we go through this. So what we're just doing here is very simple. We're saying that the data frame, remember we defined it, this is what the data frame looks like. This is DF now. Don't get confused with the names. It's just like, make sure you're following the conversation. So now we have the DF. We are saying that create another column called load. So what we want to do is that we want to have a data frame that that has temperature column and also the maximum load for that day. So, and what we are doing here is that we are dividing it by 8,000, because we want it to be in in kilowatts. Yeah. So you can see that we have it, like we have it in thousands. So it's just like, we just want to scale it down basically. So let's, oh no, we already ran that. Okay, yeah, we're still good. So let's do it here. Okay. Can you see what we have now? Is it kilo? I don't know. It's not kilowatts. Let me see. I think it was, no, it's gigawatts. Yeah. Now it's in gigawatts. Sorry, I didn't study the data set itself. It's just like jumped on this notebook as it is. So I was not quite sure. As a rule of thumb, normally when you gather your data, you look at, usually data set comes with some README. So you look at the README, you look at what each columns means. Because if like, for example, if you don't look at it or something, you don't know what does load area mean? What do you mean by estimated load hourly? I mean, you could infer, but you need to understand what all these things means. What's WHS? What's WD? I don't know. So that's your job as a data scientist. You need to like, and most data sets comes with such explanation on their, wherever they're hosting the data sets. So it is gigawatt actually, Olawale. You can see here, it's written here, it's gigawatt. So moving on. So far, this is clear, right? We are almost done with our data, with designing the right data sets that we need for this problem that we want to solve. You can see now we have the dates column that represents each day from the 1st of January 2013 till the, let me see, what's the end of it? Till the 31st of December 2017. And then we have, I mean, if we like, we can just drop this OHC column. We don't really need it. We don't need it at all. It's the same thing as this temp column anyway, temperature column. So then we have the load. So the next thing we want to do is now like to refine it a little bit. We don't exactly need all the data sets to be able to understand, to be able to predict what the peak electricity demand would be. So the first thing we want to do, actually, I mean, we could use all the data sets, which would be a classwork to you. You need to like try to use all the data sets and see if your model performed better than what we currently have, or it's performed worse than what we currently have. But what we're going to do here is that we are going to use our knowledge of, we usually know that in summer, especially in this like part of the world, when I mean this part of the world, I know most of us are in Lagos. So I mean that in Europe, in the United States, they have different seasons. It's not the same in Nigeria. Like almost every time it's like, I mean, we have Harmattan, we have, so like, I don't even think we call it summer. If you just know that we have Harmattan time, and then the rest of the year, it's almost always hot. Yeah, exactly. like Wale mentioned, it's almost always hot. It's like summer all the time for us. But it's not the same in the United States or in Europe, or like usually they have summer like right now. This is May. We are approaching summer. So it's like the sun comes and goes, and sometimes it's like it still rains and it's still cold. So we are not quite in summer yet. So you can see that their summer time, or let me say our summertime, because I'm in Germany. So the summertime is in June, July, and August. So we're just going to pick this because we know that that's we know this is summer for like we're going to assume and rely on previous data set that says like the summertime. So just make such assumption in your head, and you can say that we assume a lot of things, like not that a lot of things, but sometimes we use our knowledge of things to infer and to infer other things. So yeah, this is one of those times where you sort of like use your understanding, and then, or maybe if you're a domain expert, you use that to better make your to make your model better in some way. So if we run this now, we can see that maybe we cannot exactly see. So let me make it easier for us to see. So if you look at data frame.shape, you see that we have 8,026 rows. But now we have, if you look at just the df summer, we have 460. This is by no means the data like we use when people mention big data. This is not what they mean by big data. This is very small data, but as small as it is, it's mighty. It's doing a really good job in like trying to like predict and everything. So yeah, don't overlook small data. And it's not every time that, I mean, you need to like get very, very, very big data. Start from trying to understand correlation between some of what you have, even if it's small data. So, and so let's just plot, let's make a plot. Let's see what it looks like. So we're going to be plotting the temperature against the load. And in this case, can someone tell me what our feature is and what our label is? Okay, I'm going to ask someone. Okay, oh, yeah, please say something.
So the feature is the temperature, while the label is the peak demand.
Okay, thank you. So you're right. The feature is the temperature, while the label is the peak demand. So you can see that from looking at this data, what does it tell you? Chidima, do you want to say something? Does anyone want to say something?
Mic check.
Please say something.
So it looks like the higher the temperature, the higher the peak demand.
Exactly. For this particular summer data set, so it looks like the higher the temperature, the higher the peak demand, which is expected, you would think, because in summer a lot of people use air conditioning because it's very hot. So you might imagine that the higher the temperature, the higher the peak demand would be. So so coming down here, we want to, like looking at this data itself, how do we fit a line through this data? Like the example given here, it's like, before we even like look at this, you want to, I'm sorry, I don't have a marker or something, so it's hard to point anything, but we'll make do with this. And let's say we just want to fit a line through this data. How do we do that? We can say that maybe we can assume that maybe from the from what the slope would be, or what the intercept should look like. Oh, someone is writing something. I can use the marker. Yeah, I used it last time. So let me put it up. Let me see. Okay. Okay. This is gonna take a while because I can't find it. Anyway, so let's say we put it, just imagine that we put a line through this data to fit it perfectly, just like Kenichi has explained last class. So you can imagine that the intercept might look like it's maybe if you put the intercept around, sorry, the slope rather, we can't really infer, like we're not really sure what the intercept should look like at the moment, even though I would I might assume that, oh, maybe it looks somewhere like it looks somewhere close to less than 0, of course, because it's supposed to be on the y-axis. And if you draw this y-axis a little bit down, you can see that it's almost going to be on the negative side of things. But I don't know for sure. But the easiest thing for me to infer is that looking at this data, the way they are like clustered together and everything, what do I think would be the slope of the data? And we can understand slope a lot more if I'm just going to share my screen for a second and try to, oh yeah, I can see annotate now. Yeah, amazing. So, sure. So if you, oh, okay. So if you just look at something, let's say we have this. So, so this is 1, 1, 2. So let's say we just have that. In this plot, this linear plot that I have here, what do you think the slope would be? It's very easy to see. You can just say, like from our high school math, we know that we can find the slope by saying that maybe, so we just say y2 minus y1, right? Over x2 minus x1. Is that correct? And then we can infer from this, we can say that it's 2 minus 1 over 2 minus 1, right? And then we can conclude that the slope is 1. So for this, it means that for every change you make by 1, like it's like your rate of change is just 1. So if you go to, you can infer that if I come here and this is 3, your y would be 3. So Kenichi explained that last week. So I'm just going to assume that we are familiar with this at this at this current moment. We are familiar with it, and if we are not, please go back to look at the video from last week to make it clear. So looking at these plots, if you're asked to fit a line, what you might think is a good line is just something like this. And then maybe you assume that each slope, if you found the slope, maybe it's like going to be very, very tiny, say 0.001, for example. And so let me just clean this. Okay. Delete, clear all my trains. Yeah. Okay, so looking at this now, let's say we make a wild guess and then we say that is 0.01, which is a good assumption. Sorry, 0.05 gigawatts. So let's say we say that we get an increase of 0.05 gigawatts per degree in temperature. By the way, I think I said the temperature was in Celsius, but this looks like Fahrenheit. So yeah, you can check it out later. So anyway, let's say the assumption is we get an increase in 0.05 per degree in temperature, then that means that we can use this formula here we're saying we have a parameter theta, which is our slope, and then we multiply by the eye temperature, and then we had our intercepts. So we will make another assumption. This is just for us to do some very quick, without even using the normal, like we are not like finding parameter yet or anything. Let's just like use our maybe our intuition about what it should be and our knowledge from calculus. So if we assume that the highest, like the average demand is around 80 when the temperature is about 80, because it looks like there are lots of data sets clustered around that place. Let's say it's like our average, then we just pick the average demand to be 2.1 at temperature 80, and we just do this mathematics to find the intercepts. So let's now plot that. We now know the intercepts, we know the slope. So let's plot our assumption and look at what is, see what it looks like. So you can see this is what our assumption gets. Of course, we can do better. It's very obvious that this does not quite fit it yet, but it's not bad for an assumption, and it helps you understand what you think you know about this. So as we move forward, the next thing, our task is to find good parameters that will be able to help us fit this in a much more precise manner. And the quest of finding this parameter is why we are coming to gradient descent. So I'm going to pause here for a moment and entertain questions. Let's just pause this video. Any questions so far? Wow, this Zoom is added. Okay, yes, please. All right. So are we recording? We want to find good parameters. We already talked about parameters, how it's very good, and how it's like, it's sort of what the whole idea of learning is. So there's this thing here that says we need to define what good means in this setting. And in this setting, what's good is that we want a parameter that would help us be able to predict what peak demand would be. So that's what good parameters means here. And but in order for us to do that, we need to do so by minimizing some form of objective. And we were introduced to objective function last week, which is basically, I'm not going to spend a lot of time on this, but remember that we had something like theta 1 multiplied by some x, then plus theta 2 minus some y, and the y, let me just get my annotation to real quick. Okay, yeah. So we have, so you can, if you remember from last week, so this should be, we had theta 1 times some x. And then this is our y. And so what we're just saying in essence is that we have some mean squared error that we used last week. So we have some mean squared error, right? So this is the mean squared error, and it says that we for individual days, we sum all we find some good theta 1 and 2, that by the time we multiply, by the time we do this, we perform this operation, and then we subtract it from our y itself, we want the error to be as low as possible. The optimal error, the optimal error that we can get is 0. Like we would like to make sure that this is exactly equals to this. If this is equals, if our hypothesis is exactly equals to our target, then that means we've successfully learned good parameters theta 1 and theta 2 that can help us help us fit our data well. So let's keep going. So let's come here to talk about partial derivative. I'm not sure if we should go over this, or basically we need to. Okay, just a quick poll. How many of us understand how gradient descent algorithm works? Please use the chat if you understand how gradient descent algorithm works. If you don't, you can also put no. So no or yes. No. Okay, we have pretty good consensus. When I was going through these notes, I thought it would be a lot easier to teach this, but this is way harder than I thought. So, and yeah, so let's walk through this. Yeah.
I actually expect, because these things are similar to what we did in the last class.
Yeah, exactly.
I think, well, majority of the class, if they went through what we did last week, they should be able to understand this stuff better. So it should be more or less like clarifications on what they don't understand in this note, if they have actually gone through the note.
Yeah, I think you're right. Did anyone go through the notes? Which is going to be really, really not so nice if we don't have anyone who went through the notes. Okay. Yes, no. We went through the video. Yeah, let's just assume, Kenneth, that I don't think we have as much people that went through the notes, which is going to be a lot more difficult to explain, because the truth is that if you went through the notes, of course you would have things you don't understand, and that exactly should be what we're discussing. And I'm just going to encourage you all to go through these notes. So Kenichi, do you want to say something, or is this what you had in mind for today's class?
Yeah, so what I had in mind is to go through, not explain the concepts in depth,
Okay.
but go through it, since it's similar to what we did in the last class. Just take their minds back to what we did and then show them the similarities. So, of course, they know in the last class, we're talking about cost function, G of theta.
Yeah.
So here we are using E of theta. And I think I made mention in the class that you'll see E of theta in some places. And
yeah, Genevieve actually asked that question when we just started. She was like, she was confused. There was E, now like when she checked Andrew's cost, it was J.
Exactly.
And, yeah, so. So yeah, go ahead, please.
So even here where you're doing the partial differentiation, yeah, this is for those who want to go in depth into the mathematics, right? You can then see the step-by-step how you can calculate the partial differential of your error with respect to theta and get
Yeah.
value. But for those of us who don't really care about the mathematics, although it's important, yeah, you can just look at what the result of your differentiation is here. So I don't know, I just feel everyone should at least know what we are trying to do here. And then we'll just...
Okay. All right. So let me go through let me just run the code, and then maybe we can discuss about what we don't understand. Started good.
Yeah, it's fine.
Okay. So this is so weird, just running the code. But anyway, this was where we stopped before, right? We have the summer, we put our data sets into this data frame called DF summer that contains a column called temperature and then another column called loads. So what we want to do is that we want to normalize our data. And the reason for doing so is what was written here. So you have to come to read it. Maybe that would give you some incentive to read it. It's a very clean reason, and you would need that as you continue on this journey to understand why normalization is important. So, and running this, nothing changes. You can see it's still the same thing as what we had here. It's still the same thing as, but if you look carefully, you would see that the X and Y axis, the limit has changed. So while before we had the X-axis from maybe 50 something Fahrenheit to more than 90, now we've been able to normalize it between 0 and 1, which is a lot more cleaner. So going back, so if you want, the same gradient descent that we went through last week, and if you just like run the algorithm, we can see that we started with 0, 0, and we are updating our theta 0 and theta 1 at each iteration. At the moment, we have 101 iteration. So, and you can see that our theta moves from being 0, 0 to having this. So theta 1 is now 0.98, and theta 2 is negative 0.13, which is very close to our assumption. You know, we had this assumption that our theta 2 was like in the negative end of things, which means that like our model is not doing badly at the moment. So let's see what it looks like. So we can actually just put this into a function called gradient descent, and we put in the number of iterations we want it to run for, and we store the values of theta, and we initialize it to 0, and we just update it at its iteration. And if you look at this update function, it's very easy to see that it's the same like what we had here. Look at it. This is the gradient descent equation. We have to update it. It says that take the previous theta 1, then negate it from the step size that the learning rates that we talked about last class, then divided by the number of examples. So this is just the formula that we got this gradient formula from differentiating the error with respect to each of the parameter 1 and parameter 2. And you can see that parameter 2 does not depend on X. It doesn't have X because it's just usually we call it the bias in machine learning lingo. So your bias is usually just if you look at this it depends. It's your slope, and it only depends. Most of the time, it's like it's hugely affected by your y-axis. So, but anyway, you still have this all the each of the data point, but it's just that you're not multiplying it with an extra x. So coming back here, if we just run this, assuming you understand the like you have the formula already, you just wrote it out in code, and if we run it and we try to plot, we have a plot here, which is basically, it's just to show the normalized temperature versus normalized demand. Then we want to plot each of our gradient descent step. So if you look at the first one, this was when our thetas were 0, 0. You can see that our like the feet, this line is just it's just a constant. It does nothing. So if you look at the next gradient descent step, it jumps here. It looks like it's learning something, right? We move from this to this. Then if we look at the 5th gradient descent step, it's even moving closer. If we look at the 10th gradient descent step, it looks like it's getting close. So you can imagine like what Kenichi said, like if you're very close to the minima, it's like it will become like the updates are like it's now very small. It's not like the first one, you see you jumped from this to this for just the first step. But now it looks like it's learning slowly. After the 50th iteration step, you know, it's almost getting to its limits. Like it's almost getting to where it feels like this is how far I can fit this. Then after the 100th iteration step, you can see it feels like we can't do any better than this. If you look at this, it's like it doesn't look like it's changing anymore. So it's wise to stop. Like if as a human, if your has to fit a line through this, I don't think you can do any better than this. This feels like the optimal you can do, because it's not a perfect linear where all the data points are on one line. So you need to be able to fit the best in such a way that each of them are are considered. So including, let me show you one that looks like an outlier, including this little guy here, which is also part of the reason why our gradient descent, this line, our line rather, is also trying to fit this, trying to accommodate for this guy that looks like you know, it looks like it's probably not in the league of its colleagues here that are going through it. So it's just something to keep note of. We'll come back to that in future lessons. So if you want to visualize what the error versus iteration looks like, you can see that the error has almost flattened. Like it's not almost. After maybe like the 5th iteration, it's like it looks like we got pretty good error already. It's like very close to 0, if not 0. It's very, very, very close to 0. So if you want to look at it better, maybe we want to see how drastic the change is. We can try to use a log scale on our y-axis. And if we do that, you can see. So you started with the error going down, and then all of a sudden it's like a linear. So it's like, this is good. So these are some of the tricks you can put in your toolbox. If you're working on another data set and you need to understand what's going on, you can just like try to find the equivalent of what this looks like in your favorite library or whatever that you want to use. So yes, you can. Oh, Kenichi want to ask a question. Please go ahead.
Okay, can you scroll up?
All right. Is it this one?
No. Yeah, this one is fine, but let me use this one. Okay, so I want to ask a question. Yeah. So you can just answer maybe by using the chat, right? So at iteration 20, yeah, if we say we are going for 100 iterations, yeah, and at iteration 20, we notice that the curve is more or less kind of a straight line. What will you say about our compute if we continue training till 100? So what I mean by compute is, when you're, okay, maybe you don't know yet, but when you're training, yeah, you are using resources to train. You're using either your GPU or your CPU. And it's money if you are training it online, not on your system, right? And that time you're using to train is money that you are paying for it, right? So at iteration 20, if you notice that your loss is actually not reducing any longer, if you keep training to 100, what will you say about your compute?
If you want to answer that, just unmute yourself.
I feel there's no need training up to 100 since the error is almost constant.
Yeah, that's correct. So I hope everyone heard, yeah? So when you notice that your error isn't reducing the reduction in your error isn't so significant anymore, then at that point, you can actually just stop training. If not, you're just wasting your time, right? So thank you. I think Obiora also answered it. TJ, continue. Thanks.
All right, thank you. So, the next thing we want to do is that we want to visualize the parameter updates. We want to know how it's moving in the parameter space. And a good way to do that would be to use the contour plots, which is very informative. Yeah. So during the contour plot, you can see that this is the steps, the gradient descent step. You can see that your theta 1 and theta 2, how they are moving. They're this is the first step went from, oh sorry, you can't see my annotation. So the first step went from here. Oh gosh. Sorry, the first step went from here to here, very, very fast. Amazing. And then as it was approaching the minimum, it was taking longer time, you can see. And then it looked like as if it's getting to the minimum, it's like it's just zigzagging around here. It can't do any better. It might not have touched the exact minimum, but it's like dancing around it, and it's good enough. Like if you're supposed to, maybe this is a better plot. If you're supposed to be here and then you're around here, I mean, you're very close, right? I mean, we can say that anywhere, actually, we can almost say that anywhere around here, like here rather, it's a good, like, so you don't misunderstand me, then withdraw it. So if you have this pointed, like anywhere around here, it's like, looks like a good, like you're in the minimum. You can't move anywhere else. It's like you're already flat. When I mean you, I mean the plot actually. So moving on, you can, this is really good to understand how your parameters are behaving. In fact, if you want to have more, you want to see more contours, you can just increase the, what's it called again? Let me see. Forgot what it's called. Levels. So you can increase the levels to 50 instead of 25. So if you look at this now, you can see that you have more contours, and you can just play with this and try to understand. You should definitely consider using this, get another data set, try to understand what's going on, and make some observation, right? Like put it on your GitHub repository, write good documentation. This is how, these are the things you showcase when you are searching for jobs. People want to, like, if I want to hire you now, I want to see what projects you've done, and it doesn't matter if it looks like this. This is not a simple task. If you can go through, if you understand how this works, and you can put your code out there in a way that, and you have a readme, you can, like, a good commenting skills and everything. So whenever someone sees it, it's like, oh, this is a good project. So you should consider, doing all these seemingly small projects to build your portfolio at the moment. But make sure you understand what's going on, not just like you're just copying and pasting code. At least try to understand what's going on. So the next thing we want to do, there's something about normalization, which I'll come back to. If we had not normalized the data, our contour plot, of course, would have looked different, especially because if you study our Y and our X, you can see that the Y-axis, if I just come here to just put it out here, sorry. Yeah, it's good enough. So if you look at our Y-axis, load is our Y-axis, and our X-axis is temp, and you can see that they look the maximum and the minimum, of course. Like if you look at this temp, right? Yeah. So I forgot this. I'm not sure if this is how you do it, but maybe not. Is this how you do it? I'm so used to NumPy. I'm just gonna go with NumPy. Is this follows? Can you do follows? No. See, with the NumPy, sorry. Oh, fuck. I'm so sorry. Oh my goodness. Yeah, so you can, I'm sure there are easier ways to do this than what I'm doing, but this is what NumPy is, the thing I've been using consistently these days. This is the most accessible tool to me. So you can see that the highest for temperature is 93 and the minimum is 60. Compare in comparison was with that of load. So you can see the highest is 2.9 gigawatts and the lowest is 1.5. So the margin is too much. So what this means, Professor Zico explained this in the normalization part. So that sort of like tells you why it's important to normalize. So it says here that, and I thought I commented this out in a way to make it more obvious. So anyway, the gist of it is that if we do not normalize, our parameter can blow up really quickly, like very, very quickly. And then we would need to reduce our learning rates to be able to do it, to be able to achieve the same result. Like reducing our learning rates means that we would be taking longer to train. So something that took you very few steps, like within 20 iteration, you already got to the minimum, you're done with it, because if you're using learning rates of 1.0, literally you're taking one, like you're taking one step, like that is a high learning rate in the machine learning world. If you look at your alpha, you're using 1.0, and with that you're able to like get to the minimum. It's because you normalize your data. Once you don't, if you're dealing with unnormalized data, so that's the next experiment we're going to run. What happens if our data is unnormalized? So that's the omitting normalization. So if you come here and see you want to do gradient descent, you can see that at some point you're getting NaN. You can see that your theta 1 and theta 2 blew up really quickly. And at this point, you can't do anything anymore about it, and you've not even gotten to the minimum yet, and it's already like you already have you already have numerical overflow. So what do you do? So the next thing what you might do to help you with that is that instead of using a learning rate of 1.0, you should reduce your learning rates. Now we are taking a very, 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 very small step just to make sure that we don't miss our minimum. You know, just like Kenichi explained last week, where you're going, if you take two, where he said that if you have something like this, and then this is where you're coming, and this is where you are. So if you take too big of a step, maybe you come here the first time, you go there the second time, maybe it comes like this, and then you can start missing your minimum. If you take too small of a step, sorry, this is not the most like convex of curve I can draw, but anyway, manage it. Thank you. So if you take a very small step, maybe you go like this small, go like this small, go like this small, and you keep going small, 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 small. Of course, you get to this center, but it might take a long time before you get there. A reasonable approach might be to do small step. You go small step, you go small step, you go small step, you go small step. So this small step would almost guarantee that you get to the minimum, and you don't. And this is when we are talking about like machine learning problems that have this that behave in this that are very convex, like this convex properties, not the ones that that are non-convex. So we are assuming that we are dealing with a convex. Of course, like mean square error is convex. So sorry, this is another discussion for some other time. I got carried away for a second. Anyway, when we run this now, we can look at it. You can see that now in 100 iteration, you're not there yet at all. So you need to train for a longer time before you can be able to get the solution to converge to the minimum. So, and this is more longer time means that more resource you're wasting using Obiora's language. So it means you're wasting more compute. So now we have to wait for 1 million iteration before we can be able to get to the minimum. Anyway, and but the problem is not quite finished at the moment. So after you get your solution, your theta's are unnormalized, and what happens is that you need to be able to get getting back in the original coordinates. Of course, I mean, if you plot your theta 1 versus theta 2, then you might be able to see this clearly. But anyway, if you don't want to normalize your data, like you hate normalization for one weird reason or the other, or you just want to be able to pass in raw data and get outputs without you pre-processing the raw data first and all this stuff, then that might be a good reason to not normalize your coordinates. But you can still achieve the same thing by instead of normalizing your coordinates, you can just normalize your parameters itself. If you look at what we had before in our normalization, the normalization technique that we used was the min max, where all we did, have I missed it? So where all we did was to remove the, let's come back here, normalization. Okay. Oh, yeah. So look, if you study this, you will see that the normalized data, we just removed the mean, then we divided by max minus mean. There are a lot of different normalizing techniques. Like sometimes you could just standardize, like having in standard deviation of 1 and mean of 0, like just if you wanted to standardize your data. But at this moment, we use this min max approach to get our data into the right between 0 and 1. So if we still wanted to get the same thing that we had before, right? So we could just come here. We know that our normalized y, which is this, you can't see what I'm writing, sorry. So our normalized y, our normalized y is the same thing as having y minus mean, right? Minimum over maximum of y, minimum of y, right? Over maximum, it's harder to write here, sorry. So maximum of y minus minimum again of y. So let's just imagine that this mean of y is a, and this max minus mean is what we have by b. So our y normalization is the same thing as y minus a over b, and our x normalization is the same thing as x minus c over d, which is, it's defined here. C, again, c is the minimum of x, and d is the maximum of x minus minimum of x, just like we add in our normalizing equation above. So now we just want to do some manipulation. Say we approximate this to get to, in such a way that we want to put the mean and like this a and b in terms of the parameter instead of in terms of the data itself. So we still want to retain our normal data, but we want to use we want to make sure that our model has this effect of normalization, if you understand what I mean. So at the end of the day, when you do this mathematics, you would realize that all you're doing is that you're scaling your theta 1 by b, then dividing by d. You cannot, like, dividing is anyway. And if you look at this as well, your theta 2 is just the same as this equation. So you can rewrite your theta 1 in terms of this equation and your theta 2 in terms of this equation. So once you understand that equation, once you understand that you can do that, so the same theta 1, your theta that you get, you now change it to like a normalized version, if you can say it that way. So a normalized version of such would be b theta 1, which is from the unnormalized data, over d. So, and then if you do that, so that would sort of like give you, are we done training? Yeah, we are done training. So if I just show you what we have as theta by default, gradient descent or normalized. Oh, I wasn't printing out this theta, but anyway, so let's come here. Let's rerun this really quickly. So if you have this, and I just print out the data, you can see that we have this. So if you wanted to make it normalized version, so you can just, if you run this and still like, and then let's like print out. Of course, this is not going to, sorry, yeah. I'm retracting what I wanted to say. Okay, yeah, so now we see that it is normalized in some sense. I don't know if that's the right time, but I hope you understand what I mean. Now you're dealing with smaller values instead of like bigger values, and it's almost equivalent to what you would have had if you normalized your input. But the only difference now is that you can just pass in your temperature as it is, without first trying to, you can have a temperature, a random temperature, and then just pass it into this model, and you can be almost certain that you will get the right peak demand without you worrying about normalizing, normalizing the data, the exact one. So you can see this is exactly what Professor Zico wrote. He said, now we can use the model to make predictions on new data points in terms of the original units without normalization, which is a good, now thinking about it clearly, it's a good thing to do, especially when you're thinking about, if you don't have a separate test set or all this stuff, you just have is like new data points and you want to make a prediction without normalization. So so this is still the same thing that we had as before, of course. And gradient descent 100. Sorry. Oh, no wonder this was fast. So I knew something was not right. So at this part, this is for gradient descent when you normalized your data. Yeah, I'm pointing to my screen, but you can't see it. Interesting. Anyway, so just give me a second. This is for gradient descent unnormalized. You pass in the number of iteration. Let me look at the function again just to make sure that I'm not missing something. This, okay. Oh yeah, I see why I paused for a second. So this function is not putting x is not in as a parameter. It means that it's going to be choosing x that is outside already. So let me show you what I mean. So whatever x is outside is what we'll be using, because I'm not passing it in as an external function. So, and the x that we have here, yeah, it's unnormalized, of course, yeah. So you can see, so this is unnormalized x. So if you pass this, if you run this function, it's working with unnormalized x. And but what we have for gradient descent, the other equation is using normalized x. Can you see? It's using normalized. But like, this is not the right. I mean, I don't mean right. This is not the best way to code. What might be a lot more easier, so everyone knows what's going in or what's going on, is that to have the x as a function and just pass it in, instead of having like x here and then having x normalized. I mean, they're the same length, but it's just confusing in my opinion. And I didn't realize that when I was just running the code, but looking at it, so if you look at it, it's like it's the same thing. They are the same length. So instead of having all these extra x's flying around, just make sure that you have one x. And when someone wants to run the algorithm, you can pass in x normalize as the input. So, I mean, you can always just have some document that says, yeah, I mean, doesn't really matter. You don't have to specify that it's normalized text, but anyway, you don't have to specify. So you can have one generic. This is not the best way to document. This is just me trying to show what I mean. So if I put X here, yeah, now the same thing with error, you can just pass X. So, and the same thing with Y actually. And then you can pass Y. Of course, you should use a better name, not X or Y. You can use target or, yeah. So if I have this now, so instead of doing this, I can just do y norm and x error is taking this, and I'm passing x norm. Y. Yeah, I think we should still have the same thing. X norm is not defined. Oh, of course not. It's not. Yeah, so we still have the same thing, but now you know that you can reuse this function as you like. You can now pass in, you can take the same function and then just like say you pass in x without x norm. And then it should be the equivalent of what you had. So like, yeah, anyway, I hope that that was clear. Gradient descent. Yeah, the other thing you would also want to make sure to not put there is alpha. So you make sure that alpha is not. So like when you're trying to code, you want to make sure that you have, if you're using a function, you have everything within your function. So that's just a side note. So you don't need to keep rewriting the same function all the time. But I guess the reason why Professor Zico is doing this, or the data science that course the talk they're doing, is just to make it a lot more explicit, just so you see what's going on without any other confusion. So we've been able to see. Okay, yeah. So we stopped here. I think this is where we're going to stop for today, because the next thing that the notebook is discussing is just machine learning in general, and how all this approach that we've just learned is exactly what you need for most machine learning problem. You don't need more, like it's all about you trying to find some parameter, like most of the time, trying to find some parameter to that fits your data in some way, if you can put it that way. And most of the time you need to define an objective function. Most of the time you need to have your error, like what's the loss function. So, and you do something called gradient descent most of the time, and you iterate, you update your weights, and you know that's the whole process in a nutshell. So let me to make it concrete, let me show you like what a training phase looks like in one of the projects I'm working on. So it's just like show you that like this is like once you understand that, that's all you need. So so I'm just going to quickly share this for, okay, yeah, let me see. So if you just like look at this, ignore the rest, like the rest of the things that, yeah. So if you, oh fuck, so if you ignore the rest of the things, so if you just look at this here, this is the training phase, and you can see that all you need is that you need to have your data. I'm putting it up like because I'm using GPU. Have your data, put them in GPU. You have a data loader that loads your data. Then you have this your features and your label, and then you pass it into like a model. Like I'm now using some framework. I'm not writing it all by myself. So I already defined some model. Then you pass it in, then you get out logits. So logits is the same thing as, the screen is not shared. It's the same thing as what you had, like theta 1 times x plus theta 2. That is your that is your logits. Then you can ignore this. Then I define my loss. My loss was already defined. It's like some cross entropy loss. Then I'm zeroing the grad, which is like some PyTorch thing. And this backward is the gradient descent step thing that is doing, like it's just doing gradient descent. And then this optimization of step is the exact thing when I was updating my weights. The weight updates thing that we just did is the optimization of step. And then I'm just adding my lost item. And that's it. You can see that most of the, like most machine learning, and this is, I mean, of course, like the model is a deep learning, is a deep learning model. It's not a linear, it's not a least square regression, but it does not matter. It's still the same step that you're trying to go through most of the time, especially for like for supervised learning problems, that you have X and you have Y. So that's it for today. If you have any question, we can use the, if we still have some time, I suppose. And if you have some question, reaction, please feel free to jump in now.
All right. Hello, Ted.
Hi.
Yeah. So I just want to ask, this your notebook, will you make it available for us?
Yes, this is actually not my notebook, to be honest. I mean, of course, I ran it.
You said Kenneth said the data where they pull it from is not.
He already put it on the GitHub repository. Actually, I can share mine as well, because I just broke things down a little bit and not having them on one cell, but it's still basically the same thing. It's on the GitHub repository, and I can also put this, or just update this notebook on the GitHub repository with what I have here.
Guys,
All right,
read your mails, read your mails, read your mails. It's also in the mail I sent out, the last email. How many of you were able to even clone it, right? To even start with.
Okay, do we have any more question? Reaction, do you understand everything we talked about?